So welcome back to the Physics of Music. This time we are going to talk about some of the greatest insights in theoretical physics, some rules that help us understand how our universe works at a really deep level. And the starting point is going to be these very, very simple ideas that we talked about last time about how things operate, how things work way out in deep space or in general when you have an object that is not interacting with anything else. And so what we understood was that these objects will move at a constant speed in a fixed direction, or in other words, that their velocity in any direction is remaining unchanged in time. This was a great insight of Isaac Newton. We call it Newton's first law. And then there was another rule that says that for spherical objects, at least, these objects rotate around a fixed axis at a constant rate. And so today we're going to talk about why these rules are true. We're going to talk about a deeper way of understanding these things. And it comes from a very surprising place. It comes from thinking about symmetry. And so I want to talk about symmetry in physics, but first I'll connect with the idea that we usually think of symmetry being associated with, and that is that certain shapes have symmetry. So I want to ask, what does it mean for something to have a symmetry, like a particular shape or an object? What does it mean for that object to have a symmetry? So I'm going to give an operational definition, which might not be familiar, but you'll quickly see that it lines up pretty well with what most people think symmetry means. So my definition of an object having a symmetry is that we can perform some operation on that object that brings us to an equivalent configuration. So as an example, consider this triangle. So we would say that this triangle has a symmetry, and one way to understand, or one particular symmetry that it has, is a reflection symmetry. So we could draw a line down the middle of the triangle, and we could imagine reflecting that shape left to right, exchanging the two sides, and then you get exactly the same thing after you perform that operation. This particular triangle is a special triangle that has all of its sides equal to each other. And so it turns out that it actually has several more symmetries. Maybe you can think of one. So pause the video and see how many different symmetries you can think of for this particular triangle. Okay, well, there are other symmetries that are very similar to this one. So we could draw a line like this one and reflect across that line, or we could draw a line up and to the right and reflect across that one. But we could also think about the operation of rotating the triangle by 1/3 of the way around the whole circle, or 120 degrees. And that also brings us back to the same triangle. Or we could rotate it to the left 120 degrees, and that also brings us back to the same triangle. Symmetry is a concept that also shows up in music. So this particular musical phrase, this is part of the Ode to Joy that we talked about previously, this set of notes has a symmetry. Can you see what it is? So in this case, it's actually very similar. If we look at the musical notation, we could just swap the order of the notes from left to right, and then we get the same phrase as before. What's interesting is that this is actually a symmetry in time, because the order of the notes in the musical notation corresponds to when they happen in time. So really what it is some kind of a time reversal symmetry. We could play those notes in the opposite order, and they would sound the same as if we played them in the original order. We've also talked about the idea of a periodic rhythm, or something periodic in music. And if you have a periodic rhythm, like this one indicated by the timeline, if we imagine this goes on forever, then that is something that has a lot of symmetries. We could reverse the direction, we could reverse the order that we play these notes in, and then we get the same thing. But we could also do something else. We could shift the whole pattern forward by one beat. And so you could see that if I shift this thing forward by this one period, assuming that the period is the same as the beat in this case. So if we shift this thing forward by one period, then we get exactly the same pattern. Or if we shift it forward by two periods, we get exactly the same pattern. And so you can see that if I shift this forward in time or backward in time by any number of periods, we get exactly the same pattern. So this is kind of like if you're in a band and if the drummer has a very simple part that repeats every measure, and if the drummer somehow loses their place and is off by one measure, well, then they're going to basically sound the same as they would if they were playing the correct thing. Of course, in real music, usually the drummer is not just playing exactly the same thing every measure. So we've talked about symmetry as an operation that you can perform on something that brings it back to an equivalent configuration. And now I want to talk about symmetry in the context of physics. So I'm going to talk about the symmetry of that the environment of a physical system might have. So we talked about the environment of outer space, of empty space far away from everything. And that will turn out to be a very symmetric environment. So what does it mean for an environment to have a symmetry? So again, what we want to imagine is taking this environment and somehow performing an operation on it. It's a little bit hard to do that. So it's often easier to imagine that we're in the environment and then we perform an operation on ourselves. So let me give you an example. The first example is going to be similar to the one that we just talked about with the rhythm, except that it'll be a spatial shift instead of a shift in time. So imagine that you're in this environment of infinite empty space. Now you move yourself to the left by some amount, maybe 4 meters to the left. And what you would notice is that the environment looks exactly the same as it did before. And so we would say that the environment of empty space has a symmetry under a shift of 4 meters to the left. Well, you can see that it has a symmetry under any shift in any direction. So it has a lot of symmetry. Okay, so this is the idea of symmetry of an environment. We're going to talk about more examples later on, but first I want to tell you about why we care about these symmetries in physical environments. And the reason we care has to do with a beautiful result in physics, I think one of the greatest results in the history of theoretical physics. And this is a result of a very important, but I think not as well known as she should be, theoretical physicist named Emmy Noether. She was a mathematician and theoretical physicist. She was a contemporary of Einstein and lived from 1882 until 1935. Unfortunately passed away because of cancer. So what Emmy Noether showed is that for every symmetry of a physical environment, there's going to be a special quantity, some kind of physical quantity that we say is conserved. And what that means is that this quantity is forbidden from changing with time. Okay, so I want to go through several different examples to show you how powerful this kind of idea is, the idea of a conservation law in physics. Okay. So the first symmetry that we're going to talk about is the symmetry of an environment that is unchanging in time. So that would be an example where you could imagine, let's again stick with the environment of infinite outer empty space. And so if you observe this environment and then you shift in time, meaning you just wait for some amount of time. So an hour later, the environment is exactly the same as it was before. Everything would behave in exactly the same way. Okay, so this environment of infinite empty space has what we'd say is a time shift symmetry. And so then what Emmy Noether's theorem guarantees for us is that there's this quantity that is not going to change as time progresses. So if you have now a physical system in that environment, there's going to be this particular quantity that is guaranteed to stay the same. And this is the quantity that we call energy. Okay. So if you have a time-independent environment, then any physical system in that environment, to any such system, we can associate this quantity called energy, and that energy won't change. Okay. So I want to tell you a little bit about what is this energy, what is this quantity for the simple case where we just have a single object in say, this empty space. Okay. And so first, let's imagine that the object is just stationary. So it turns out that in that case, the energy of the object is exactly the same concept as what we usually refer to as mass. Okay, so the idea of mass, this is a very, very famous thing that was realized first by Albert Einstein. The idea of mass, it turns out, is just the energy of an object when it's not interacting with anything, when it's far away from everything, and when it is not moving. More specifically, there's a kind of conversion factor that allows us to go from the usual units of mass, say kilograms, to the usual units of energy, which would be joules, and that conversion factor is the speed of light squared. So you take the mass of the object in kilograms, you multiply by that, and that is how much, that tells you exactly how much energy it has when it's not moving or doing anything else. Okay. So let's just understand then, what does Noether's conservation of energy idea then imply for this particular case? So what it would say is that the mass of an isolated object cannot change with time. Okay, so this is a very important result that we're going to use in the next part of the talk. So we know that objects can be moving or rotating as well, and so turns out that when you have a moving or rotating object, then the total energy of that object can be understood as this mass energy that we just talked about, plus some extra contributions. And so the energy from the object's motion is usually called the kinetic energy of the object. If the object is also rotating, then it could have what we'd call rotational kinetic energy. So that's basically all you need to know about energy in the context of these isolated objects in outer space in these very simple environments. Just as a more interesting example of what energy conservation would do for you, this would help us analyze even more complicated situations where instead of just one isolated object, your physical system might have many objects, and they might be colliding with each other. Maybe some of them break apart, and you can have multiple, maybe more objects than you started with. And so what the conservation of energy will tell you is that if you just add up the energies of everything before, their mass energy and their kinetic energy, and then you look at the final situation, the sum of the energies of all your final objects has to be equal to the sum of the energies of the original objects. Okay, so this is a very powerful result that we'll see many times in this course. So now I want to move on to the next example of a symmetry and the next example of a conservation law. So the next example has to do with this symmetry that we discovered earlier, the spatial shift symmetry. We noticed that if you were in empty space and you moved to the right or the left or up or down, then everything would look the same as before. Okay, so according to Noether's theorem, then there should be an additional set of conserved quantities. So because you could move in any direction and things will look the same, then there should be some conserved quantity associated with each of those symmetries. What is this conserved quantity? It's the thing that we call momentum. So the shift symmetry of empty space leads to the idea of the conservation of momentum. So you might be less familiar with the notion of momentum, although it's a very common word in everyday language. And so the momentum of an object in a particular direction turns out to be closely related to the velocity of the object in that direction. So, for example, in the picture here, we have an object. It has a mass m. It's moving to the right with speed v, and its momentum is defined to be the product of the mass and the velocity. So this is the momentum of the object to the right. We can also talk about the momentum upward, and in this case, because it has no velocity upward, then the momentum upward is 0. Okay, but what does this mean? What is momentum? It is basically, in practice, the momentum of an object tells you how hard would it be to stop that object from moving. Okay, so you could see that if you had two objects moving at the same speed and one of them had more mass, then the more massive object is definitely going to be more difficult to stop than the one that is less massive. Similarly, if they had the same mass and one of them had a larger velocity, then the one with a larger velocity is going to be harder to stop than the one with a smaller velocity. Okay, so we will understand quantitatively and precisely exactly in what sense this is true in later lectures. Okay, but I just wanted to point out that this idea that momentum is related to how hard it is to stop an object, that lines up pretty well with our usual use of the word momentum, where if you have momentum, it means you're on a roll with something and you're likely to continue on with whatever it is that you're doing. Okay, so now I want to connect back. Now that we understand that this conservation of momentum is guaranteed by the symmetry in outer space, I want to connect back to our rules for physics in outer space. Okay. So we've understood that because of the conservation of energy, that the mass of an isolated object doesn't change with time. And we've also understood that because of the conservation of momentum, the mass times velocity in any direction of an object can't change with time. And so what we know is then that the velocity in any direction can't change with time. Okay, so using conservation of momentum, which came from translational symmetry, and using conservation of energy, we actually now have a deeper understanding of this rule of Newton's first law, that the velocity of an object in any direction is constant, that it doesn't change with time. Before I go on to the final example that I'm going to talk about with symmetries and conservation laws, I want to give you a slightly more complicated example. I want to give you an example of an environment that has certain translational symmetries, but it doesn't have all of the translational symmetries of outer space. Okay, so I want to imagine physics near the surface of the Earth. And so what you notice is that if we're here on Earth, then moving horizontally is basically a symmetry. Moving horizontally in some direction, we kind of expect suppose for simplicity we're just in like a flat plane and there's no interesting geography. And so then things would pretty much look the same moving horizontally. But if you try to move vertically, then things are definitely going to be different. You're further away from the surface of the Earth. You're further away from the center of the Earth. And so it's definitely not a symmetry anymore. Okay. And so let's understand how this observation kind of interacts with the idea that momentum is conserved when you have a symmetry. So because we have a symmetry under these horizontal translations on Earth, what we should expect is that momentum in the horizontal direction is conserved. Okay, and this is true at least in the approximation where we kind of ignore air resistance, the air molecules are also things that break the symmetry. But let's ignore the air for now, and then we would find exactly that the momentum in the horizontal direction is conserved. But what about momentum in the vertical direction? Well, we know that that is not conserved near the surface of the Earth. If we throw something up, then its velocity is upward, but then it stops and then it comes downward. And so this vertical momentum is just not conserved. So at least we can see that in this case, we don't have a symmetry translating in the up-down direction, and that lines up with the idea that momentum is no longer conserved. Okay, so to finish, I want to talk about one final type of symmetry and the corresponding conservation law. And the final kind of symmetry that we have is a symmetry of rotations. And so that would be that if you're out in empty space again, and you rotate in some direction, any direction you want, everything is going to look the same as before. Okay. According to Noether, there should be another conservation law because that's a separate symmetry than with the ones we discussed. And this other conservation law that we have is called the conservation of angular momentum, or sometimes the conservation of spin. And what is spin? What is angular momentum? Well, this has to do with rotations. And so the spin or angular momentum of an object is related to its mass, its size, and its period of rotation. And so the conservation of angular momentum would then say that if you have an object which is of a fixed mass and it's not changing its size, then it will just continue to rotate with a fixed period. So it'll keep spinning at a constant rate. And this explains the second rule that we had for physics in outer space. And in particular, it explains why the day that we have is always the same amount of time. It always takes the same amount of time for the Earth to spin around on its axis. Okay. So that's pretty much it. I'll just throw out one little tidbit of information that ties in with some of the work Einstein did. And so a very, very interesting thing that Einstein realized and wrote about was that there's one more kind of symmetry that we have for empty space. Einstein realized that if you, instead of just moving or waiting or rotating, if you actually start traveling at some velocity in infinite empty space, that again, everything would look and behave in exactly the same way as before, as if you were stationary. And so that's an additional symmetry of nature. And this led to his entire subject of special relativity and these crazy ideas, well, true, but crazy ideas about time and how people traveling at great velocities and coming back would have aged less than other people and so forth. Okay. So that's all for this lecture. Next time, we're going to start talking about more interesting environments where you have interactions where momenta can change, and we'll be able to make even more interesting predictions for how physical systems behave.